Hello! Today we'll be discussing our feedback controls project. We're group number 13 and our objective was the Levitator. Alright, so here's what we're going to talk about today. We're going to go through our project description, including design goals, our control principles, our prototype components. We'll list out each type. And we'll go to the controller description before we show you our stellar system demonstration. And finally, we'll wrap things up in a nice conclusion. All right, we're going to start things off with our project description. Our main objective here was to design and build a magnetic levitation system that can suspend a small object below it at a small distance from the solenoid. We'll go into more depth on that later. Next, we're going to go through our design goals. Our first one was to build a rigid frame insusceptible to vibration, a working solenoid, and an ideal object to levitate, which we ended up choosing a small metallic ball. Next, we wanted to design and implement a sensor to track the position of the levitated object and provide feedback. Then we wanted to design a control system of analog circuitry, digital circuitry, or both to process feedback and control the solenoid. And lastly, we wanted to apply theory from our wonderful feedback controls class to model and mathematically describe this wonderful process.
Alright, so the control principles. We're talking about the ideal closed loop poles. This is how we want to have our system in theory. So what do we want to have? We want to have the zeros at the left half plane, so we have stability. What else do we want? We want a fast dynamic response with no overshoot. That leads us to a critically damped response, which means that we will have two repeated closed loop poles in the left half plane. We use a controller to adjust Kp and Kd. We only have a PD controller to set the loops and place the closed loop poles in this plane. This is how we thought our process could look like. We have two sensors down here that we subtract from each other, and a set point that we both feed the error function into the controller and have the solenoid transfer function, which then leads to the actual distance of the ball from the solenoid. This is our setup. We have the solenoid here, the photodiodes, two lasers, the MOSFET, the potentiometers to read Kp and Kd on the fly. We have the Arduino controller here, and the op amps to amplify our sensor signal. Alright, so now more in detail about the special components, starting off with the solenoid. We use about 400 feet of 24 gauge wire. We use a screw as our iron core to enhance the magnetic field, and also we have an adjustable mounting to adjust the height of the solenoid. Now our first part of our sensor, the photodiodes and the laser. We have two lasers powered by the 5 volt output of the Arduino, two photodiodes that the set point is set up like this, so the ball just breaks half of the beam of the upper sensor, of the upper laser, and half of the beam of the lower sensor. So this is our equilibrium state, we could say. The signals are both fed into the Arduino, so we don't subtract them analog but digital. The op amps. With the op amps, we amplify the sensor signal, so we can monitor it better and calculate better with it. We power them with an external voltage source, with 9 volts. The decisive part for the amplification is the resistor ratio between the resistors here, here, and here. It was kind of a try and error process that we did, and we came up with this combination, which allows us really to read from 30 bytes ambient light to 1023 bytes when the laser points at the sensor and is not blocked. These are just the potentiometers. We used KP and KD. Also, we have a third one to simulate some inputs that we needed in the testing stage, but we decided not to take KI in order to improve the stability of the system. All right, the solenoid driver is just a regular MOSFET that we connected like this, drain to the solenoid, source to ground, gate to the PWM Arduino output. So depending on what signal we send to the gate pin, we will get different current running through the solenoid. And also, as we can see it over there, we had to put some heat sinks onto the MOSFET because the heat dissipation was very high. Our current range was from 0.4 to 1.5 amps. We see just the voltage source that we powered the solenoid with. So how we thought the Arduino should work is we first subtract the set point from the feedback that we get from the sensors. Also, the sensors are subtracted digitally in the Arduino, so part of the sensor work is outsourced into the Arduino. So we get an error function after that, after the subtraction with the set point. Then we calculate the error function, provide the PD control in the code by the PID function, which we have to import from the PID library. Read the potentiometers and plug them into the settings of the PID function. And then we control the MOSFET with the PWM output of the Arduino. In the circuit diagram, here we have the op amps that amplify our sensor signal from the photodiodes over here. We have our 3 potentiometers where we use 2 to read KP and KD. This is our MOSFET, our PWM output, ground, and the solenoid. This is pretty much the setup. And now we'll show you a short video how our system is actually working. This is our serial monitor. Here we can read top value of the sensor, bottom value of the sensor, read the variables, KP, KD, and monitor the output. Now we want to test what happens if we block the bottom laser first. Of course, it makes sense that the output rises and we get a higher current than before. Instead of 0.8, we get 0.95 amps. That's with an output, PWM output of approximately 130. If we have 255, we can get an output of 1.2 amps. If the top laser is blocked, of course, we get an output of 0, and the current is still 0.8. Now we try the whole thing with our levitated object, and we see it's clearly pulsing, but it doesn't have stability. You can see the pulsing also at the current that's changing.
Alright, that wraps it up for our presentation on our Levitator project. We faced many problems, including our solenoid was too weak and we had to remake a new one right before the project was due. And our large group made communication very difficult between group members, and a lot of people didn't know what was going on in crucial parts of the project, and that made it very difficult. Things we could have done differently: we could have tried a different sensor. We could have tried a Hall effect sensor with a more even solenoid that would have made measuring distance a little bit easier. And we need a larger current difference from when our bottom photodiode was blocked and our top photodiode was blocked. Right now we currently have 0.2 amps, but we need probably more around 0.6 or 0.8 amps. And we could have used one laser instead of two lasers.
Ich hoffe, es hat euch gefallen. Gebt uns einen Daumen nach oben. Bis zum nächsten Mal.